SwayamPrabha. Digital India. Educated India.
Okay, so far we have seen this kind of a signals flown domain, and now we'll see its effect on the system. Okay, so this is how so one can ask this a fair question to ask. Okay, if we are saying the Shannon reconstruction reconstruct the signal back in the frequency domain by using this kind of a filter, which is the T is a scale for the signal, and it is like ideal kind of a filter. Okay, it's a rectangular filter which is sharp cutoff kind of a filter. If we see this in the frequency domain, okay, this kind of reconstruction, what is the kind of filter that we are applying to reconstruct this back? Okay, it's nothing related to a signal, like what are the samples. No, it has nothing to do with what are the samples. It has something to do with how we reconstruct the signal back. Okay, so this in the frequency domain represent some filter of this sort. Okay, so this filter is having this kind of a representation in the frequency domain. Okay, how that comes we'll not get into, but I mean just to kind of give some feel that okay, it is not, if it is not ideal reconstruction, then what it is. Okay, then this is the answer that okay, it is a reconstruction of the sort, and okay, it is kind of allowing some values beyond this omega is over 2 also to get so something if it is existing for the signal when it is sampled. Okay, you may have something coming in this domain also, no? Like even if the signal is not aliased, okay, there will be some part of the signal coming here. Okay, that signal will get also getting some representation when it is done in the 0 order volt kind of domain. Okay, that is a kind of a meaning one can think about. So this is a filter. Okay, so one has to have a little bit of a sense of when we talk of filter. Okay, see, this is a sense that we talk about, right? The filter is filtering in the frequency domain, allowing some signals to pass through, and some signals are completely not allowed to pass through. Okay, so say when I say the filter is of this form and rectangle kind of a form, then this particular kind of a filter function in the frequency domain multiplies by frequency domain response to produce the output of the filter. That's how one can think about. So it's like a input which is getting into a transfer function, and then transfer function is modifying that input and producing some output. Okay, so every system from that perspective can be seen as a filter also. Okay, so this is nothing but a frequency domain response of a filter. Okay, so transfer function, what is the frequency domain response? When you have a transfer function, what is frequency domain response of a transfer function, or frequency domain representation of a transfer function? Or when you substitute S is equal to j omega in the transfer function and get a magnitude and plot it, what you get?
The Bode plot.
It's Bode plot, right? Exactly.
Yeah.
It's like a Bode plot of a system. Okay. So this filter is nothing but a Bode plot of the transfer function of that filter, basically. The frequency domain response of this filter is nothing but the Bode plot of that filter. I mean this kind of a sharp cutoff filter is I mean it's impossible to realize in the mathematically completely. But if it has been there like that, it is kind of arguments that Shannon has given actually. So this filter transfer function, okay, its frequency domain representation is giving you this kind of plot, which is board plot of that whatever transfer function. That is a filter transfer function. And when you pass this sample signal, okay, through that filter, means like we are multiplying the frequency response of that sample signal by the frequency response or frequency representation of a filter function or board plot of the filter function to produce this graph. That's the idea of filtering, or it's the same idea when you have a input given to the system in the frequency domain, and you pass it through the transfer function, or this transfer function, the input is given to the transfer function, and transfer function is producing some output. Okay, then this, say suppose the input is a sinusoidal frequency, simple sinusoidal input, then it will just get scaled by the transfer function form, and that scaling will be dependent upon what is this response or board plot of that transfer function. Okay, that's the kind of idea that is there for the filter. It's the same idea as you have an input represented in the frequency domain, transfer function represented in the frequency domain, and output coming as a frequency domain representation. Okay, so the two are not different. The filter is not different from any kind of transfer function kind of a thinking in board plot domain. Okay, so that is a important kind of a concept. When we say, okay, I want to filter this signal, so we need to think, when moment you say filtering of a signal, you need to typically think in the frequency domain first to kind of get my filter. Okay, so we'll talk about a little bit about filter a little later in more detail. So right now we are just kind of looking at the signals, and we are filtering some of these signal and to show that okay, the channel reconstruction will be reproducing this signal completely back. But now if you see, instead of channel reconstruction, I had this the reconstruction which is zero order hold. Then see, this is omega 0, this is omega s by 2 frequency here, and this is omega s here. You remember that frequency domain response was going up to omega s. So some part of this function will also come up in my filtered kind of a signal, or in my signal represented as a zero order hold form. Okay, so see, some of these are one has to be very clear in the mind about which domain you are thinking. Okay, if you start thinking in mix up the domains of thinking, then typically I've seen the confusion arises. Okay, so we are clear here that okay, we are thinking only in the frequency domain, and in the frequency domain we know that zero order hold has some kind of a form that is plotted up here. This is a frequency domain zero order hold kind of a thing, will go like that. Okay, and when it is like this, then what will happen to my signal is what I am thinking in the, so I'll get some warping of this triangle to happen. So instead of this triangle getting produced reproduced completely like this, I'll get this kind of a warp, because this is not really a rectangle kind of a window, and then the additional part from this signal also will show up in my form. Okay, so one can kind of think, okay, well, this is how it will get plotted in the frequency domain. That's a frequency domain representation of a signal which is having a zero order hold. Okay, so see, this is again a frequency domain representation of a signal which is sampled, just sampled. Okay, so this is just sample signal, and now we are seeing from the sample, when we do some kind of a reconstruction, what is this frequency domain representation is what we are kind of considering here. Okay, so sample signal we already know has this kind of a multiple replica of the original signal frequency domain response coming up. But what we are looking at further is that okay, if I now have those samples represented as a zero order hold, then what is going to be for that kind of a reconstruction, what is the frequency domain representation? Okay. So although that has not much of a physical value or like implementation value in some sense, but it's kind of just good to know that okay, for this such a kind of a zero order hold, there is the signal, if it has triangular kind of a representation in the original frequency domain analog signal, then it will get represented in some kind of a warped way when it is sampled. And not just sampled, they are sampled and made a zero order hold like that. Okay, so this is important, not just sampled, but sampled and reconstructed as a zero order hold. That is a very important statement. Otherwise, if just a sample signal, it will have just some mirror images. Okay, so there is a subtle difference between the two. So the warping in the frequency domain is happening is somewhat kind of like indication. I mean, one cannot really, get what you say intuitively seeing that okay, oh, this means it will be warping. No, it will have some difference. It will have some kind of a warping, but we cannot predict exactly what will happen. Only by doing this mathematics, one can kind of be able to say, okay, well, exactly this kind of a part is getting multiplied by this, the straight line, if it is, if at all it had been a straight line, right? See, this straight line, what we are saying, the triangle is just our kind of a sense of representation that the signal has a contents up to that point. But even there, those things are going to get kind of somewhat disturbed. So the signal contents at different frequencies are getting disturbed in some sense when I say it is warped. So let's move further then. So now we just see some small application of sampling theorem. Like now, how do you think about a system? Say for example, if you are like developing a mechatronic system, typically before getting into sampling, you use this low pass filter. Okay, now you use this low pass filter to make sure that beyond certain frequency the contents are made zero. Okay, otherwise if you take a generally like a analog domain signal and see its frequency contents, you'll find the frequency contents to go all frequencies are represented in some way. Okay, so to make sure that higher frequencies are completely chopped down, you use this low pass analog filter. Now this analog filter, you know that you can use some simple RC circuit to kind of get this analog filtering done. And now once you do this, then one can think about, okay, now if I'm sampling, see if you want to really preserve all the contents of your signal and make sure that okay, you are representing your signal really in a better fashion, this is a way to do stuff actually. Use this analog domain filter, but you cannot have analog domain filter with a very low cutoff. Okay, because with a low cutoff, you may get into either you may lose some part of your signal that you want to kind of preserve, or what will happen is like the first order filter does not have a sharp cutoff. These RC filters are first order filters. They'll have a slope. Okay, so that slope will allow some frequencies in the higher than the cutoff also to pass through. If you know 1 over tau s plus 1 is a transfer function for the first order domain system, then its mode plot is simply like you get by using this tau corresponding to tau. 1 over tau is your cutoff frequency, and beyond the cutoff frequency you will have a 20 dB magnitude. I mean the slope cutoff will happen there. Okay, so that slope is what is going to cause some of the higher frequencies also to kind of come beyond cutoff. Those frequencies will come and get represented. Okay, so you typically require ideally sharp cutoff filters, but then sharp cutoff means your cost is going to increase. Okay, you cannot use simple RC circuit to kind of get sharp cutoff filter. Okay, so RC circuit will give you only the first order kind of a cutoff. So this first order filter you used and sample now your signal frequency with a larger frequency, so that some of these signals which are getting passed beyond the cutoff frequency, they also get represented in this high frequency, large sampling frequency will preserve those frequency contents, and then the signal is further processed for any operations, so that it will get completely. So you can have multiple kind of operations that can be possible beyond this point. So the idea here is to use first analog domain filter. So you don't kind of directly get into a sampling given a signal. Okay. So given signal, you know what is the frequency content that you are of interest to you, and use that as a cutoff for your RC circuit to develop, and use that circuit on board before the signal is taken into your microcontroller. That is the idea. And once it is there in a microcontroller, you sample it at a relatively high frequency, and so that all the contents are kind of preserved. Okay, and then you can once it is contents are preserved and there you are, then you can take a call based on the frequency response representation of the signal what to do. Okay, you can use some kind of a digital domain signal, digital domain filter to further filter the signal and things like that. Okay, some kind of a further processing can be done easily, and one of the ways is this. So you have this signal of interest here. It is represented typically by our triangle kind of a representation, and then there is a white noise, okay, which is of all frequencies. Then you use this, it's called anti-aliasing filter. Okay, so this analog domain RC filter is typically used, and then you can get the signal representation at the point 2. So you can think, okay, look, with the RC filter, what will be then the signal representation in the frequency domain at this point will look like. Okay, then for this is one of the examples. So you should be able to kind of given this filter function, one can see, okay, what is the frequency domain representation coming out. So these are all, I'm not naming this axis, but this is a filter frequency domain f of j omega of the signal, and this is omega axis and things like that. So this all, whatever is represented here is all in the frequency domain. Okay, so all the signals which are coming out here, they will be represented as a frequency domain signals. Okay, so here there will be a representation where the original signal will be there, and then with the sharp cutoff with the anti-aliasing RC filter, you'll get this signal beyond this point tapered down some value here. So this 20 dB sloping cutoff will kind of taper the signal off from here to some value which is very less. It will not be kind of a constant going over like that. Okay, as the frequency increases, this filter will have a effect that it will lessen the higher frequency signals completely. It will completely chop off the higher frequency signals or taper off the higher frequency signals. And then when you sample it, then the samples will be represented in some way. Then you can see that, okay, how these samples, after sampling, how the signal is going to look like, and how, with what frequency I should sample, so that this, this tapering off part does not get mixed with this the signal itself. Okay, the signal of interest we need to preserve under the sampling. Okay, so after sampling is happened, you know that, okay, this whatever this original signal frequency response is going to get replicated or mirrored multiple places at omega s kind of a frequency. Okay, so we want that when that is happening, we don't want these high frequency components to come into the domain of the signal of interest. Okay, so that is what we want to make sure of this. So I would suggest you ponder over this example, and actually start writing these or sketching this signal represented in frequency domain at these multiple locations, and then see whether how the things are making sense. So these are very different operations. There is an anti-aliasing analog filtering operation is happening here, then sampling operation is happening here, then you can have some kind of a sharp cutoff digital filter is given here. So this is like some kind of a digital filter. Ideal, I would say. It's not like practical filter, because we cannot have like very sharp cutoff practical filter possible in digital domain also. So if that is there, what is the signal representation up here? And there is this something called downsampling. Okay, so this downsampling just means that you skip the samples. So you have original signal sampled at say frequency omega s, then the downsampled signal by factor of 3 will be the same signal when sampled at frequency omega s by 3. Okay, that's what it means actually, the downsampling. So what you do is out of these multiple samples, you take one sample, omit 2 and take third sample. Then take omit 2 again, take next third sample. Like that you can keep on doing that. So you omit the samples in between. Okay, that's how you get a new signal which is downsampled. Why you need a downsampling is to kind of save the memory. Okay, so if you have not downsampled the signal, your lot of samples will be stored into your memory. Okay, so downsampling should not see this downsampling sometimes may create some kind of aliasing effects. We don't want those aliasing effects to be created. So then what you need to have this cutoff frequency for the sharp cutoff filter to be properly adjusted. So those are all the engineering points to be worked out as an engineer. You will oh no, this downsampling may not work. I will downsample only by factor of 2, or I'll have to cut off this to much lesser frequency so that this downsampling does not produce aliasing. Those kind of thinking is what I'm calling as some kind of engineering that needs to be done. So the fundamentals for that are all there. So far we have talked about. It's the application here to kind of see how one can process this signal to finally get it in a form that is used in the control application. Okay. So beyond this, or beyond this point, or even after sampling, you can start using the signal for control purposes. No problem. You don't need to kind of sharp cut off these and then do this operation at all. So you do just analog filter and then sample it high sampling frequency, and you'll be good to kind of go. Or you may say, okay, I need to remove this some kind of parts on the sample so that I can have a better processing possibility with the downsampling. Then you do these additional steps and reduce your number of computations and things like that. Okay, so this is one of the examples of how do you start thinking about sampling and use that in a typical mechatronics kind of a domain application. Okay. So I think we may not have much time till we go today, but so next part is what we talk about is say suppose we have this. So I'll just give you a flavor of this. We will not get into a lot more details here, and we may kind of come to the point where we need this e to the power. We had this question somebody has asked at e to the power a matrix power of exponential of a matrix. Where do we need to? Where we want? Where we need to use that? Okay, this is the place where we use that. Okay, so the question here is really if your actuator is getting the signal of this sort. Now we know why the actuator will get a signal of this sort. Okay, so this signal is received by actuator, then actuator will be implementing this signal on the plant. Okay, just amplified version of the signal on the plant. Now, under such scenario, how my plant is going to behave? Okay, so My plant is not really receiving a continuous input, but input is now received in this kind of a sample and zero order hold kind of a form. Okay, so this question is what we need to answer here, and for that we consider our system solution trajectories. Okay, the systems in a continuous domain, like if we represent this signal system as a state space system. Okay, so we know what is state space representation now. Okay, so with the state space representation of the form x dot is equal to ax plus bu, and y is equal to cx, only up to that, we don't consider du kind of a form in that. So x dot is equal to x plus bu and y is equal to cx. In that kind of a form, if I sample this signal, or the input is given in this kind of a form to that signal. So when I say I sample this system, means my input is going into this kind of a form. Okay, that's a terminology that typically people use. Okay, this is a sample system. Okay, or this is a continuous system, or this is a sample system, or digital domain system. So if I have my input going in this kind of a fashion on my system, then how my system is going to behave is what I want to derive mathematically, and that's where I start off with the solution of a system in this form, where you have this homogeneous part of the solution, and then you have a particular integral part of the solution. Okay, these both the forms are there, and x0 is like your initial condition, and this is how like your solution of the system of the form x dot is equal to ax plus bu will be. Okay, so now when I have, so this x is typically a vector here, and b is again a vector, and we are considering only single input to this system. Okay, u is a single input that is going into the system. Now, if I want to see that this form is implemented, u is of this kind, where u is constant over the time period 0 to t, t to 2t, 2t to 3t, like that u is constant. So this is I can call this as say u1, u2, u3, like that. I can give some kind of discrete kind of values to u. Under that scenario, what is going to happen? So now my system is say at some point here integral xk kind of a value, and I want to see what is my system, how my system evolves over with the constant input given here as uk till that point, like xk plus 1. Okay, so what is my xk plus 1? Okay, xk plus 1 of t. Okay, when I start at xkt. Okay, so this is my xkt. So I use the same form. I have started with the initial condition xkt here, and then its evolution from now time over time, which is t is starting from 0 to t here. Now which is kt to t here. Okay, so this k plus 1 t minus kt will be there. So kt to k plus 1 t is what is the evolution I am looking at. So here evolution is from t is equal to 0 to t is equal to small t. So like that, when it is t is equal to kt, to kt is equal to final t is equal to kt plus k plus 1 t, this will be the evolution. Okay, that's what I am representing here. Okay, this is a homogeneous part, and the interesting thing will happen over this part. Okay, now this u of tau is going to be a constant value here. Okay, between the values kt to k plus 1 t, you have a u of tau to be constant. Okay, so say 2t to 3t, u of t is equal to u of 2t is equal to constant. Okay, so that is a value that is constant here, and that constant will come out of this integral, and I get this so in a much simpler form like this. Okay, so sorry, where is that? Okay. So what I'm going to get here is so e to the power at here. So this is a matrix. If you see k plus 1t minus kt, it is going to give you e to the power at, and x of kt here. Okay, so now I'm dropping this capital T to kind of make the life a little simpler. So instead of this capital T, I will just keep it as k plus 1. So x of k plus 1 is equal to e to the power at times x of k plus now this integral from 0 to t, if you shift this, the time axis is shifted, then you get this simplification here. 0 to t, e to the power some variable s here, as, b and ds. Okay, so this s is some other variable that is used to replace this tau. Okay, so so this is, and this is given here. What is this s variable, and all these things are given more detail here. So you get these two matrices here now. Okay, and this is where you get this your e to the power at function here, and one can now start representing this x of k plus 1 as some function which is now a characteristic function for the system. This doesn't have anything related to k, and this is also doesn't have anything related to k. These are like characteristics functions, characteristics matrices of the system, which are going to give you the system in the digital form. Okay, so this is a form the system is coming into. X of k plus 1 is equal to phi of a t. Now this function is a function of sampling time t, and then this is a psi of a t times u of k. Okay, so this is a form that you get for your digital system. And yk is equal to c times xk. This remains the same. There is no change in this form. Okay, and then these matrices are defined here. Okay, and now this opens up completely new domain of analysis for systems in the digital form. Okay, x of k plus 1 is so you can transform the system from your analog domain to a digital domain by using this kind of a zero order hold kind of a form. Okay, so this is what is happening when you use in MATLAB also while converting the system from analog domain to digital domain. If you use that zero order hold kind of option, then it will do this precisely. Okay, so I think maybe this is enough for us to stop here. I mean, there is a good amount of discussion that can happen further about how do you now use this digital domain. So this is the most important crux of how do you go from analog domain to the digital domain. Okay, very nicely from physics, understanding the physics of it. I mean, many times people just say, okay, you just use Z domain transfer function. But what is a Z domain transfer function? How it comes? Where is it? Genesis of it happens. So those are kind of parts are where this part is very important. So this x of k plus 1, if we get into the Z domain representation, or this Z transform domain representation, is Z transform of x of k plus 1 is z raised to 1 times x of z or some. So we'll not get into that detail, but basically this is some kind of a shift operator that is happening. Okay, shifting of the signal with one sample. So x of k plus 1 is equal to z x of k. Okay, that is how one can see in the Z domain. Okay, so that kind of operators can be introduced into this form to get now a new transfer functions in the discrete domain. Okay, so this is what is the next step that is done, and all that now we can develop this domain of digital systems, and all the tools that we have, root locus analysis or this Nyquist analysis, you will find some equivalent representation in the digital domain. That you can have a transfer function in the digital domain, and then you can define some new conditions for the stability of the transfer function in the digital domain, and things like that. All these things can be slowly developed further. Okay, so that is what this digitization of the system starts giving you all these kind of multiple tools at your hand to do the analysis. So if for some reason you cannot use higher sampling time, See, most of the time when you have analog controllers, you use higher sampling time and you will be fine. Okay, you will not be so bad in implementation of control and things like that. But whenever you feel that, okay, oh no, I must use like lesser sampling time, okay, then you may need to trigger the digital domain analysis of their system to make sure that you whatever your designs are not kind of getting any worse performance out of your system. So one can think in the digital domain itself and design controllers in this domain itself to make sure that your system will work even if your sampling is a little less. So that typical figure for the sampling frequency to be is it should be at least 4 to 5 times more than your closed loop bandwidth frequency. Okay, that's like a ballpark figure one can based on experience or how it comes, one can do a whole greater analysis about that, but ballpark figure is about 5 to 6 times more than your closed loop bandwidth of the system should be your sampling, then your controller will get implemented properly. Okay.